All right, we've just got a binomial on question 6 on mine. Are you guys ready? Set? Take notes? Ask questions? Be engaged? Enjoy factoring. It's just a bunch of fun. A game is no fun if you don't play. So let's play some factoring. Because this is a binomial. I'm going to be looking for a pattern if there is one after we find the GCF. So step number 1 is find the GCF, i.e. greatest common factor. I see a 3 and I see an x. There's only one factor of x, so that's all I can take out. Take out, quote unquote, divide out, factor out. I'm undistributing, because if I distributed 3x over what I get in here, I should come back to the starting box. So 3x is x squared, left. Hello, Mrs. Fisher speaking. I do. Yes. Thank you. Bye-bye. Okay. And then 3x. You could do this mental math. I'm just showing you what my brain sees. Plus 3 goes into 6 2 times. And x cancels x. There's my remaining binomial. So step number 2 is find a factor pattern. So after greatest common factor, you only have, let's see, 3 patterns that have a binomial. Let me show them to you. I sit still, right? Okay, I'm looking on this side. You see these 3? The top one is a squared minus b squared, and the bottom 2 have cubes. And our problem we're looking at just has a squared. So, and both of them have to be squared with a subtraction. There is no sum of squares. So this is a yes. There's a pattern with the first term squared, but this is a no, because there's no patterns. Hit it once, didn't hit it again. Okay. There are no patterns that have a sum of perfect squares, and that's not a perfect square. So you can make that, you make that judgment like this, right? You can say no, because you know those things. And I'm just mapping them out why it's a no. So you're done. Step number 3. There's no factor pattern after the taking out greatest common factor. So this is step 3. Write the factored polynomial in your software. So I just put in 3x parenthesis x squared plus 2. And you'll get to be such a factor master that you will spot it immediately if it fits one of those patterns. But it takes practice, doesn't it? And that's what we're here for. Yesterday, Sydney, we made a little quick list of perfect cubes because when there's a cube here, that might be a cube here, and you can always check, using your calculator to find the cube root of this number. So I can check to see if it's a perfect cube by taking 5/12 to the 1/3 power. That's like the fastest way to get a cube root on your calculator. Okay, and you could have them, just listed. I could list them over here again for the day. 1 to the 3rd, 2 to the 3rd, 3 to the 3rd, 4 to the 3rd, 5 to the 3rd, 6 to the 3rd, 7 to the 3rd, 8 to the 3rd. Isn't that neat? 5 plus 1 plus 2 is 8. 9 to the 3rd. They all have like connections. I love connections. And 1,000 is 10 to the 3rd. So those are, you could just sketch them out and then you'll notice. But first, step number 1, 100% always look for a GCF. I could say look, or I could say find. If there's not one there, that's okay, but I always look for a GCF. So when I have a leading coefficient, they're both even. This guy is 8 cubed. 64 is 8 squared. Let me get my calculator out. Does 64 go into 512? It sure does. So if I would not have found the GCF right away, I would have broken down those two terms into factors, but I would still be wrong because they're not factored completely. You might have caught it later as well, but get her done right away, and then you've cleaned up your act. You're ready to do step 2, find a factor pattern. And if you notice, that's a perfect cube. That's a perfect cube. The difference, there is a pattern with the subtraction. It's called the difference of cubes. And it's interesting, to say the least. And I haven't memorized, obviously, because I play with it every day. It's just my happy place to factor. So I pay attention. Okay. Let me show you it in the The back of this book is like Algebra 2 on steroids. It's got everything you need, be college and career ready. Okay, right there, you see that second to the last one? I get to take that guy and put it into this form. because this side is the expanded form and this side is the factored form. And if I distributed this out, all the terms will fall away except for the first term and the last term, and that's a beautiful thing. So let's tackle that for our values instead of just A and B. Okay. This is x cubed minus 2 cubed. It's kind of handy to write it as a cube. Then when you go to put it in the pattern, you take the cube root of the first term, take the sign of the binomial, take the cube root of the second term, and in this pattern, there's only one subtraction sign. Even if you're summing cubes, there's one subtraction sign, but it's not here. When you're taking the difference of cubes, there's a subtraction sign to start off because these two should match. And then the rest are pluses. Okay? So this first term has to be what times x is x cubed? X squared. So the first term is the cube root squared. Plus the second term is the first term times the second term of your cube roots, but you don't double it. And the sign doesn't come with the 2. Okay? And the last term has to be 2 times what is 2 cubed? That'd be 2 squared, which is 4. And don't even try to factor anymore because they won't factor. This has not been doubled. It won't be doubled. And you'll always be done after you're all done with greatest common factor and factor patterns. You're always done when you create these two factors for a difference of cubes. Rest assured, this is finished. This is done. And if I multiply this all back out, don't want to forget my 64. That's an easy mistake to make, is forgetting the greatest common factor you took out. That's why it's really important to write everything down in steps vertically when that 64 comes down. And this is what you'll enter into your software. That's step number 3, right? This one right here is a result of step number 3 because you just wrote your factored polynomial. You guys making sense of the signs, the terms? Where do they come from, and why do we need that, the signs we have? Why do we, all that stuff? You guys need to make sense of that in your own mind. So it isn't just me giving you the meal. You guys are making the meal yourself. If you want to have an analogy of eating food. Eventually, I need you to make this meal yourself. Done with number 7? Everybody has it written down. No wait. No waits. Okay, number 8. Now I'm just going to write down the polynomial. Remember the steps. It's a binomial. Look for a GCF. See a factoring pattern. Difference of cubes. write your factored polynomial. Please ask if you have a question on where I got what. It's all a process that lets us factor polynomials. Probably too late, I'm sure. Larry. Number 9. You just never know what's going to show up. I love this one. Are you taking notes, gentlemen? Okay, 2, 9, and 7 have absolutely nothing in common, but they all have an x squared. We've got something new. There's a leading coefficient other than 1. So that means you're going to play the bottoms up game. I love this game. You have factored earlier in your algebra life, I hope. And there's many methods to factor a trinomial that has a leading coefficient other than 1. This method has, for me and many others, Mrs. Meyer uses it too, I'm sure the other algebra teachers use it, that it's guaranteed with the least time, like it's so efficient and so accurate. Hopefully you will like this as well if you've never seen it before. If you can find the correct set of factors, usually when I was growing up, I just tested and checked and moved them around and played around until I found the combination. If I didn't start in the right direction, then I would take me longer to get to the end. This one, you get to there every single time. It's crazy how it works. All right. Bottoms up means you take that leading coefficient and you make a pretend polynomial by multiplying it to the end term. So this guy is a pretend. It's called pseudo polynomial. So my pretend polynomial that I'm going to factor is x squared plus 9x plus 14. So instead of having the leading coefficient higher than 1, I just have myself that common polynomial where I can ask myself what factors of 14 add up to 9. 1 and 14, oh bingo, 2 and 7, beep, 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 beep. There we go. So I write my factors. I have my x plus 2 times x plus 7. But remember, that's pretend. Now this is how you go back to real. I multiplied a 2 to the end. Now I'm going to divide it back out again. so it shows up in front. So this is the real factored polynomial. I have my x squared from up here. Way up there. Yeah. Okay. Then I reduce x plus 1. And then you see this 7/2 can be reduced. I just move the 2 back in front of the x. So there the 2 goes back in front again, and you are done. So if you didn't do this, you would not have, come to this conclusion right away. You would have had to play with the factors of 2 and 7's combination that added up to 9. So instead of doing that, you make a pretend polynomial where you were guaranteed, you put it, bottoms up, back to the final result. It's beautiful. It works every single time. Every single time. It's beautiful. I can't even go over, I can't rant enough about this method. It works so sweetly. And these are the kind of polynomials that make people hate factoring, because they take so bloomin' long to factor. Unless you use that bottoms up method that is so smooth and sweet. It's just, I hope we get another example of that. I don't know if we will, but note number 9, if you're not familiar with the bottoms up method, you want to practice that because it is so efficient, okay? And nobody likes to play a game that takes too long, right? Okay, we're on to number 10. Got time for this one. I think this one's a short and sweet one again. Yeah, we'll get this done. 11 is on that other video too, so x cubed plus x squared minus 42x. Yeah, this is just a common one. Take an x out. Factors of 42, negative 42, and added give me 1. Did you know 3 goes into 42? Nothing yet. 4 doesn't, 5 doesn't, but 6 does. There's my magic pair. It's not magic, it's math. And we're done right on time. I'll leave that up there. And you can keep going if you want, but at least have through number 10 done on your homework, okay? For tomorrow.